Okay, so this vector VB can then be represented something like this part was shown here. Okay, so any questions here? I hope it is clear to everyone. If you have any, you can raise your hand. Okay, then if none, then I will proceed further. Okay, so when I introduced you to the gradient, divergence, and curl, I escaped one thing, and it was to explain the derivatives. Okay, because some of you may not be familiar with partial derivatives. Okay, ordinary derivatives you obviously are, but the partial ones you may not be able to perceive right now. So I will try to go into that a little bit. Okay, why? Because I will be needing it uh, at the next point. Okay, so suppose you have a line, okay, the purple line shown here, and you want to get the slope of it, okay. So first thing that we observe here, that this line has got a uniform slope all over, okay. Slope does not change. So if you take 2 points, x1 y1 and x2 y2, and take the slope between these 2 points, okay. So slope means it will be given by the value of tan theta. So that will be given by y2 minus y1 divided by x2 minus x1, or we simply write it delta y over delta x. Okay. So this slope remains constant all over the line. Okay, it does not change. So it does not matter whether you take slope between the points here and here, or you take slope between the points here or here. Okay, it remains almost same. So the slope between these 2 points x1 y1 x2 y2 has this value, okay, and it is uniform, it remains the same. Next we can take one more curve. Okay, so suppose I have a curve uh, which is varying arbitrarily, okay, like this. So this is fx, which varies with x, okay, x, or maybe x and y. Okay, and now if you consider the similar points x1 y1 and x2 y2 here, then and you take the slope, okay, you take the same kind of change that you evaluated previously, then you can see here that this slope here, the change, okay, delta y over delta x, this won't be giving you the exact value of slope over all the points, okay, between x1 y1 and x2 y2. It will kind of give you an average slope between these 2 points. Why? Because the function has a shape because of which the slope is actually varying at all the points. Okay, so if you consider slope, it could be given by the tangent here. Okay, if you consider here, then the tangent direction will be different. Okay, similarly here, the, the tangent direction will be different from the previous one. And so this way, the slope of this function is changing between x1, y1 and x2, y2. So if you take delta y over delta x, it won't be giving you the exact value of slope. It will rather give you an average slope between the 2 points. Okay. So how is then the slope calculated? You know it already. Okay. So how do we calculate it? What we do is to consider delta x to be very small. What does that mean? That we consider 2 points which are very nearby, x1 y1 here, then x2 y2 probably here. And in that case, if I try to zoom this area, so if you have x1 y1 here, and suppose the nearby point x2 y2, so you can see that this function is nearly a straight line in that case. Okay, so for very small delta x, this change in y or delta y, okay, can be given with a straight line. So for that very small delta x, we define delta y over delta x as dy over dx at this point. So to calculate slope of an arbitrary function fx, we calculate dy over dx, and this is actually the ordinary derivative. Okay, so this you have already known from your previous classes. Now we go for the next function. Okay, so suppose I have a function z, okay, and z depends on variable x and variable y. So z can be said to be a function of x and y. Okay. So if you want to look at it in the real meaning, okay, so z could be the height which varies with x as well as y. So this can be represented with the curve shown here, the 2D curve that you see here on the screen. Okay, so there are a few things which we can notice about this curve. That suppose I am at this point here, x1, y1, then you can see that this function is actually changing slowly as you go along x. However, the function changes more rapidly, okay, or more quickly as you go along y direction or as you go along this direction, okay, along y. So we have got one slope along x-axis, whereas the slope is completely different along the y-axis, okay. So here we have two different slopes, one along x, one along y, and if you take any other arbitrary direction, then the slope will obviously be different, okay. So for such kind of functions, I already have defined gradient. I hope you remember what gradient gives. So the gradient gives the direction of maximum change of the function. Okay. So let's forget about that here. So this height z changes at different rate in different directions. It means if you want to give the change or rate of change of this function, then that rate of change cannot be given with df over dx or df over dy. Okay, then you need at least two derivatives, or the rate of change of this function or change in function cannot be given with a single derivative. Okay, so in that case, what we do is to define rate of change in x direction, and for that you I hope you understand here that we need to keep the value of y to be constant. Okay, y should not be changing when we are defining the rate of change along x. Similarly, when you define rate of change along y, then you should have x fixed. So such slopes can be given with del z over del x, or we also represent it like del z over del x with y kept constant. Okay, so this y superscript here, subscript here, it says that it is kept constant when you are taking the derivative. Okay, so the variation of the function or the slope of the surface at a given location along x direction, it can be given with del z over del x. Similarly, the variation of function along y-axis, okay, or the slope of the surface along y-axis is given by del z over del y with x kept constant. Okay, so sometimes you do not just write this x kept constant here with uh, this line and x. Okay, we normally go for del z over del x. So del z over del x obviously means that all other variables like y, they are kept constant when we are taking the derivative. Okay, so if in that case you want to have a general change, okay, or change in value of x as you vary x and y or x or y, so that change in z can be given by the rate of change along x-axis multiplied by change, okay, small change along x plus rate of change along y-axis multiplied by the change that we are doing along y. So for that case, we can consider a simple function like z given by 6x square y plus 3x plus 5xy plus 10. And then you can calculate del z over del x. Okay, so when you calculate this derivative, you consider y to be a constant. Okay, and similarly, you can also calculate del z over del y, where you will keep this x constant. Okay, so yeah, that's all. Yes, Siddharth.
Sir, I was asking this question. If we want to calculate the gradient, then how we will do it? Because I am not able to understand the difference between slope and gradient.
Slope and gradient.
Yes, sir.
Okay, so actually, slope we normally define along one particular direction. okay,
Yes, sir.
or for a function of one variable like fx, okay. And if the function is of two variables, then we define slopes along two different directions like we are doing here, okay.
Yes, sir.
So in that case, we take del z over del x. So here we are keeping y constant, and if you take along the other direction, then you are keeping the other variable constant.
Yes,
Okay.
sir.
So same way, you can define slope, or actually the direction of maximum change of a function like t x y z, where t is actually depend t actually depends on three variables x, y, and z. Okay.
Yes, sir.
So in that case, if you define change dt like I shown here,
Yes, sir.
okay. So here I have only two variables x and y. So similarly, you can extend it for three directions. Sorry, three variables. So that will be del z over del x into dx plus del z over del y plus dy plus del z over del. Sorry. Uh, okay. So for that you need to consider some other function like f or t. So del f over del z into dz. Okay, and then I wrote this dz change in terms of the gradient, okay, dot dl. And then I interpreted df. Okay, so what was df? Could you remember now? What does this df give then?
Gradient.
So what's the physical meaning of it?
The maximum rate of change of slope.
Right. So this actually is pointing along the direction where maximum change happens. Okay, along the direction where maximum change happens.
So
Whereas
if we
this dz could be any arbitrary change in any arbitrary direction. Okay, so like
the gradient is rate change per length.
yes, gradient is also a derivative,
Change
but
per
we
unit length.
define, yes. So this is defined in the direction in which maximum change in the function is happening. Okay,
Okay, sir.
like I took the case of a mountain. If you are standing like at this point here, so if this mountain height is given with z, which depends on x and y, so at this point here you can see that the maximum change in z will happen in this direction, okay, not in this direction.
Yes,
So we
sir.
can say here that the gradient of z will be defined in this direction, in the direction of this hill surface. Okay, whereas
Okay,
you
sir.
can take and change along even this direction. Okay, the
Yes, yes, sir.
surface may
Yes.
not be very plain, so you can take any change in this direction or in the direction which is along the hill. Okay, yeah,
Okay, sir.
yeah. Please mute yourself then.
Sir, one more thing, sir.
Yeah.
Sir, you have told us theoretically, okay, but sir, in one question you also show it how to do it practically, but how to do questions on that gradient in
Uh,
some question.
yes, I have given you the question, right? Where's the question? This one, right?
Yes, sir. Sir, but
Okay.
here was slope.
Yes,
Here it was slope, not gradient.
yes. The height of certain hill, and where is the slope? What do you
Sir,
mean?
in third question, third
Yes,
part.
yes, yes. Third part. How steep is the slope? Okay, at point 1 mile north, 1 mile east. Okay, yes. So it is the maximum slope. 1 mile north, 1 mile east.
Sure.
It
So
is
gradient is the maximum slope, na? But if we have given maximum slope, then it means
right,
gradient.
right, right,
Okay,
right.
sir. Okay,
Yeah.
sir. Okay. Thank you, sir.
Okay. Please mute yourself. Okay, so same way you can try to plot other functions, or you can try to understand these partial derivatives. Okay, we can also have a 3D surface, though I cannot show it here. Okay, so then you can go for those things, right? So it's okay here. Yeah. Okay, so sometimes the variable x and y in the function f x comma y, they can also depend on other variables. Okay, x and y can also depend on other variables like u comma v. So we can then say that x is a function of u and v, and similarly y could also be a function of u and v. Okay, so in that case, if the variation in u and v is known, okay, if we know how u and v change, then we can find change in x. And same way, if we know the change in x or y, x and y, then we can find change in z, the function f here. Okay, so to find or to write the change in z, we know we use what we know as the chain rule. Okay, so in that case, this change in z with respect to y, okay, this can be given as del z over del x multiplied by del x divided by del u, okay, plus del z over del y multiplied by del y over del u. So what does it signify? So the first term here, del z over del x, okay, it is actually change in z or change in function f with respect to x, and this del x over del u gives you the rate of change of x with u. Okay, so the first term represents change in x due to change in u, which is given by del x over del u multiplied by change in z due to change in x. Okay, so same way we can define the second term, and it is a product of change in y due to change in u, and then multiplied by change in z due to change in y. So this is the change of z with respect to u that we can write. Similarly, you can also write down the change in z with respect to v. So this is del z over del v. It will be del z over del x multiplied by del x over del v plus del z over del y multiplied by del y over del v. Okay, so this is actually called the chain rule. So if you have some function z which depends on x and y, and then these x, y also depend on other variables like u and v, then the change in z can be given with these equations. Yes, Siddharth.
Sir, in previous slides, sir, please go that.
Yeah. Yes.
Sir, here it must be half now, half of that, because if we cancel dx by dx, then it will become dz by du plus dz by du.
No. It does not go that way, actually.
But sir, in chain rule, we do that only. Na? We multiply and divide by dx, so it becomes two separate differentiations.
Okay. So, what are you studying in mathematics nowadays? Do you have this differentiation or differential equations, etc.?
No, sir. In 11, 12, that we have done that.
So yeah. But you may not have studied this chain rule there, right?
No, sir. We have studied chain rule there, sir.
Is it?
Yes, sir. But and in that only if the function is du by dv and both functions are in x and y, then we generally do this only. That we multiply and divide by dx and then differentiate both of them.
Okay.
So that's why I was asking like that.
Yeah, it's not that way actually.
Okay, so it is different.
Yeah, it's slightly different, and maybe in your mathematics class next semester you will understand it. Okay,
sir. Yeah.
Okay, so next we have the directional derivative. So in this case, we were taking the derivatives or change along x-axis, okay, along x direction or along y direction. Now we can take change along any arbitrary direction like ds. Okay, so suppose we want to find change in z as we move by some distance delta s. Okay, and this delta S distance is along some arbitrary direction. We are not moving along X, we are not moving along Y. And then I hope you now can recall how we defined gradient. Okay, so that was also a change along with a change along any arbitrary direction, delta S. Okay, so this delta S could be in any direction. In 1D, we know that this delta X could be either positive X or could be negative X. Okay, or negative Y or positive Y and things like that. Okay, so with that, we defined or the change is given by the directional derivative. So this derivative here, df by ds, is given by the chain rule that I have introduced here. So this df by ds is basically del f by del x into dx divided by ds. I hope you now understand this term. Similarly, plus we have del f by del y into dy with ds plus del f over del z into del z over del x. And this arbitrary change delta s, okay, it could be in any direction. So we can write it like we did in case of Cartesian system earlier, that this, ds could be given by some I into dx, I cap into dx plus j cap into dy plus k cap into dz. And if you then want to write the value of ds, so I hope you will understand that this ds can be given by square root of dx square plus dy square plus dz square. Okay, so at this point I can take an example. So we need to find the directional derivative of phi, which is a function of x and y given by x square plus y square at a point 1, 2. Okay, so you will have this function plotted, and I have already done that. We have already seen this function. Okay, I hope you calculated gradient of it. So you can see here that this function is actually a cup-like function, or could be a cup-like function if you draw it even further. And then it has got a minima somewhere. And if you go along x or along y directions, then this function is actually changing at different rates. Okay, it's not changing at the same rate. So we'll try to define the directional derivative. So what will that be? Directional derivative phi. So if I define d phi, okay, in some direction, say ds, then that d phi over ds will be given by del phi over del x multiplied by dx over ds, okay, plus del phi over dy into dy over ds. Okay, and I hope you understand here that this s here could be a function of x and y, or we can say this x and y could also be a function of s. So this directional derivative is given by this equation then, and we will now try to find out what is del phi over del x and del phi over del y. So you have this phi given by this equation, and when you calculate del phi over del x, so you obviously consider y to be constant. So this del phi over del x will then be 2x. And then we have this dx over ds, okay, plus this del phi over del y is 2y, and then you have this dy over ds. Okay, so next what we do is to try to find out these values, the values of dx over ds, dy over ds, and for that we can actually do with or we can in general write this d phi. Okay, so let's now write it. So next thing that we can do here is to consider this direction in which we have to calculate the directional derivative. So the direction is given by I plus 2j. Okay, so if you give this direction by I plus 2j, then and then you try to plot it. Okay, so suppose I draw here x and draw y here. Okay, so this I plus 2j direction will be given by this I vector, and then we will add the 2j vector. Okay, so this I plus 2j is represented by this line here, which goes something like this. And if I want to write an equation for this line, I hope you can understand that this can be given by y equals 2x. Is it okay? Or is it opposite? Or x equals 2y? Just find it out. Okay. So in that case, then you can find out the value of dy over dx. Okay. And that value will be given by 2 here. Okay. So for this I plus 2j, we have already seen that the equation could be something like y equals 2x. Okay, then we can calculate the value of dy over dx. Okay, and when you have this value of dy over dx, then in the equation where you needed dx over ds, this can be calculated. Okay, so how to do it? We know this ds has got a relation with dx and dy. So this ds is actually given by square root of dx square plus dy square. Okay, so then you can have this ds over dx. You can divide both sides by dx. So it will simply be 1 plus dy over dx square. Okay, and then you will find the value of ds over dx, because you know dy over dx from this equation here, which is 2. So similarly, you can also calculate the value of dy over ds, and then you put the value in that directional derivative df over ds. Yeah. Okay, so yeah, you'll have to do this calculation, simple calculation yourself. And yeah, is there anything, Piyush?
Yes, sir.
Yeah.
So for the point 1, 2, we have taken the equation of line y is equal to 2x, because this point may be found in any other line satisfying 1, 2.
No, it's not one.
It's the position vector of that point.
Yes. Yeah. Right. Find direction at the point 1, 2. So we have also given the directions here. It's not just 1, 2. You see the directions here? I plus 2j.
Yes, sir.
Okay, so that's a line, right? Or you can give it with a line.
Yes, sir.
So on this line, you have to find out the directional derivative. ठीक है अभी? So
yes,
same way, can you do it for the next part? For the second part here?
Yes, sir.
Okay, yeah. Thank you. You can mute yourself. Okay, so this is all about the derivatives, ordinary, partial, and directional derivatives, and I want to use them now. So I will have. So I have introduced them. Okay, so is there anybody else? Yeah.
Sir, how did you write ds is equal to dx square plus dy square whole root?
This I already told. A infinitesimal length element in Cartesian coordinates. Okay, how is it given? You remember? I cap or x cap into dx plus j cap into dy. Is it okay?
Oh, okay,
and
sir.
Yeah, then you
The
can
ds is an arbitrary function in function, right, sir?
It's a infinitesimal displacement vector, okay, in Cartesian coordinate. Similarly, if you write it in cylindrical coordinate or in spherical polar coordinate, then it comes in terms of r theta phi or r phi z. Okay.
Okay.
So this is an general infinitesimal length element or displacement. Okay, and then its magnitude can be given by the square root of dx plus. Okay, yeah, who's next? Sorry. It's not easy. Lower hand. Abhishek, anything else? Sorry. Abhishek, yeah.
Second one also, I didn't understand first completely.
Okay, so what could you not understand?
So after that ds under root x dx square plus under root 2 dy square.
Dy square.
Yes, so what we did after that?
We divided both sides with dx. Okay, so was it okay? Dx square plus dy square here? And when you divide with dx, you will have this whole thing divided by dx. Is it okay?
Yes.
And if you take it inside square root,
yes,
we will get the square of it.
Yes.
So here we have dx square plus dy square.
Yes.
And then divide by dx square. So dx square by dx square will be 1 plus dy over dx square. Is it okay now?
Yes, sir.
Okay. Now that. What else? Yeah, I will lower your hand, unmute.
Sir.
Who is it? Yeah, Anil Chauhan. Yeah.
Sir, in previous that you can take y is equal to x. How is it, sir?
Y equals to x.
Yes.
That's what the question is. Could you try to plot this and just try to find out the line? Okay. It could be a simple, easy home assignment for you. Okay. Just see if it is y equals 2x or 2y equals x. Okay. Because I'm not sure about it. So just confirm to me tomorrow. Will it be okay?
Okay.
Yeah. Okay. So we can then introduce these gradient, divergence, and curl in other coordinate systems like cylindrical and spherical systems. Okay, so if you want to write down gradient in a spherical system, then gradient of t, any function t, is given by del t over del r cap plus 1 over r del t over del theta cap plus 1 over r sine theta del t over del phi into phi cap. Okay, I hope how it was written in Cartesian coordinates. So sorry. In Cartesian coordinates, this gradient of function t is given by del t over del x into x cap plus del t over del y into y cap plus del t over del z into z cap. So then we can convert it to a spherical system and cylindrical system. Okay, it's actually easy to understand how we can write in a spherical system or cylindrical system the gradient. Okay, so I'm trying to explain it for gradient. So if you convert the Cartesian system, or you take it to a spherical system, then instead of x, y, z in Cartesian system, you have r, theta, and phi in a spherical system. Okay, and similarly in cylindrical system, you have s and then phi and then z. Is it okay? So with that, in a spherical system, we should have something like del t over del r plus, so del r is basically a small displacement along r direction. Del r is a small displacement along r direction. Similarly, in the next, you should have displacement along theta direction. Okay, so if you write it like del theta, as I told you earlier, it's not actually displacement, it is an angle. Okay, so a small displacement along theta direction that we know is given by r into d theta. Okay, so instead of having del t over del theta, you should have del t over r d theta. Similarly, a small displacement along phi direction. Okay, so that is given by r sine theta d theta. So instead of simply having del t over del phi, you should have del t over r sine theta d phi. Okay, so similarly, you can use it for cylindrical systems. However, if you try to define gradient and curl, it's not that easy. Okay, so normally if you have if you get a question relevant question in the exam, we'll be giving you these expressions for divergence or curl. But if you want to evaluate them, if you want to find them out, then I'm telling you the method. Okay, so in that case, we can write this function del t over del x like del t over del r into del r over del x plus del t over del theta into del theta over del x plus del t over del phi over del x. Okay, so and then next thing you do is to put the value of del r over del x, del theta over del x, and del phi over del x. And for that, you have relation between x, y, and z, okay, with r, theta, and phi. So you will, from those relations, you will find out the value of del r over del x, del theta over del x, del phi over del x, and then put those values here. Okay, so like I can probably give you the first relation. So how is r connected to x? Remember it? How is r connected to x in a spherical polar coordinate system? R equals x square plus y square plus z square. Is this okay? So in that case, if you calculate del r over del x, how much should be the value? It should be simply, we then consider y square plus z square to be y and z variables to be constant. So we will have this x square plus y square plus z square raised to half, and if you differentiate it, then you should get the same term with minus half. So you will have 1 over square root of this thing into differentiation of x square. So that will be 2x. So same way you can calculate del r over del y, okay, which you will have in the term like dt over dy. So same way you have another term dt over dz. Okay, and all those will be written with the help of the chain rule. okay, which is mentioned here. So in all of them, you will then have this del R over del Y here. You will calculate the value from this equation. Similarly, del R over del Z, the same from here. Okay, so this way you have calculated this first term. So you have del R over del X, which is 2x divided by you should also have a 2 here. So a square root of x square plus y square plus z square, something like that. Okay, into half. So same way you will calculate the value of theta, del theta over del x and del phi over del x, and you will put those values here, and then finally you put this del t over del x, del t over del y, del t over del z for the gradient del of t, okay, or grade of t. From that you will get the relation, okay, for a spherical system or cylindrical system. Okay, so is there anybody here? Yeah, Shubhrant.
Yes, sir. I have a doubt in the previous slide.
Previous
in the directional differentiation.
Here. Okay.
Yes, sir. Here we can take, sir. We have to take the directions according to the vectors which are given.
Right.
And also, sir, the equation which we will form should pass through the point 1, 2.
Right.
Okay, sir. Then I was having that doubt only.
Yeah. Okay.
It should be point only.
Because we are taking derivative at this point.
Okay, sir. Thank you, sir.
Okay. So this way you can write the values of gradient, divergence, and curl in cylindrical and spherical coordinate systems. So these values are given in Griffiths, and you can have a look at them. Okay, at least if you do not want to actually calculate these values, so just have a look at them, how they appear. It will be good if you try to calculate or evaluate those values. Okay, so next thing that we want to introduce here is line integration. Okay, let me check the time before that. So line integration of a vector function has the expression like a to b b dot dl. Okay, so this vector v here is integrated along a particular line, okay, along a particular path. P means path here, that goes from point A to point B. And this vector v can actually change the direction. Okay, so what we will do is to divide this path into a small element, a small dl elements, and then take this b dot dl at all those points for all those elements, and then add them up. Okay, so that addition is simply the integration, b dot dl integration. So this is integration of a vector v along a path that goes from A to B along some line, okay, along some arbitrary line, arbitrary shape line. So v here is a vector function, dl is infinitesimal displacement vector, and integration is to be carried out along a prescribed path p from point A to point B. Okay, so the path in the question can sometimes form a closed loop. Okay, so in that case, we will have this integration performed from A to B, then from B to A, if it is forming a closed path. So in that case, this integration is represented with this circle symbol on the integration symbol. Okay, so this means a closed integration or integration over a closed loop. So the integration will be performed from A to B, and then if you have a closed loop means you will have a path like this. Okay, so A to B, B to A, or B to A to B. So for that, the integration or the line integration is simply represented by B dot dl, the closed loop integration. So at each point on this path, we take the dot product of B with the displacement dl to the next point, and the most general example that you know is f dot dl, okay, which is nothing but work. Yeah. Okay, so we can take an example here. So suppose you have a v function given by y square x cap plus 2x y plus 1 into y cap. And then you have to find out the line integration from point A 1 1 0 to point B 2 2 0, and we have the paths given along path 1 and along path 2. Okay, so what is path 1? Path 1 is to go from A up to this point. You can define it like C along x-axis, okay, along x direction. So along this path, obviously, you will see that the y will remain at a constant value. Okay, so if you go along this path, then during this segment first of path 1, this y will be constant. It means dy will remain 0. Okay, along segment first. And then when you go along segment 2, segment second, then obviously along this segment, x will remain constant, so dx will be 0. Okay, so dl, the general length element we know is dx x cap plus dy y cap plus dz z cap, and path 1 consists of two parts. The first part has dy equals 0, the second part has got dx equals 0, and we have no variation along z-axis, so it means that dz will remain 0 for both these paths. Okay, path first and second segments of path 1 as well as path 2. So we can write down along path first, okay, or first segment, that this dl will simply be given by dx into x cap, and then we have this y, corresponding y, okay, which has value of 1. So if you then write down v dot dl, so v, we have y square x cap plus 2x y plus 1 into y cap, okay, dot dl. dl is how much? dx into x cap, okay. So then you have dot product of v with this thing, and then you know that x cap dot x cap is 1. So we will have y square multiplied by dx, and then y cap into x cap is obviously 0. So this v dot dl is nothing but y square into dx. Okay, and as y equals 1, so it will simply be 1 square into dx or dx. So this v dot dl is equal to dx. Now you have to find out the integration along this segment first. So how to give it? It will be v dot dl integration, and the integration will go from x value of 1 to x value of 2. So it will be 1. Same way you can do along this path here. Okay, so for that we have x which is fixed at 2, and if x is fixed at 2, then obviously dx equals 0. So in that case, this dl here will be given by dy into y cap. X equals 2, you will calculate v dot dl again. So y cap into y cap term will give you this 2x y plus 1. This x cap into y cap term will be 0. So then you have to you can put the value of x here. So x equals 2, so 2 into 2 will be giving you 4, and then you have y plus 1 into dy. And if you integrate it now, with y going from 1 at this point to 2 at this point, so that integration should give you 10. And now if you try to write down this whole path integration along path 1, so what is it? This path integration will be integration along first segment plus integration along the second segment. So that should give you the sum of the two integrals that we have calculated here. Okay, so same way you can try to calculate this path integration along AB. Okay, and for AB you have to use a little trick. So what is that? You can see that y equals x along path 2. Okay, so in that case this dx will be equal to dy, and dz is obviously 0. So you will then write down dl. Okay, dx equals 0, so you will have dx x cap dx y cap, and you calculate v dot dl. Similarly, you can also calculate the integration. So I will try to stop here because you have got your next class. Yeah, we are already overshooting. So if there are no questions, then I end my class here. Oh, sorry. Yeah, Anishwar.
Sir, is there any tutorial? Is there any demo class? For this,
tutorial, yeah, tutorial will be there. Today there will be tutorial.
that oh, you will send the mail, sir.
Did you have tutorial yesterday?
No, sir.
No.
No.
Okay, I will check again. You should have tutorial now in this week. Okay, so I will check with Dr. Roy again and we'll schedule it. Okay.
Oh, okay, sir.
So yeah, yeah, you can ask the other questions tomorrow. Okay, so that is why I'm trying to end here because you have another class.